Hi everyone. So this video is all about presenting some of the digital twin work we've conducted in the research activity in mechanized mining systems. My name is Luke van Eyck, and this digital twin work was focused on estimating traction in real time for a skid-steered ultra low profile vehicle from CMTI. So I think best way is to just jump straight in. This is the vehicle we're talking about. So as you can see, it's skid steered. For those of you who don't know what that means, it means your wheels don't articulate to steer the vehicle. Instead, they rely on differences in rotation speeds of the different wheels to rotate. So perhaps, let me just grab a marker here. So you'll see this wheel set was rotating in that direction while the other wheel set might be rotating in the opposite direction to get this thing to turn. So that is skid steered. Now, the important properties for what I'm going to be showing today is that this vehicle is electrically driven, so it has an electric drivetrain, and each of the four wheels is independently controlled from the electric motors. This specific machine is designed for underground roof bolting operations, and this is relevant because there's no GPS underground, and we'll get to that a bit later. And then finally, as I've been mentioning, this is a skid steered vehicle. So yeah, based on these facts, let's continue. The key question for this project was how we can estimate traction between this machine and the surface it drives on. So why should we care about traction in the first place? Well, firstly, there's big safety implications to knowing the traction of this machine. Firstly, this machine, as I mentioned, is designed for underground operation, and in the specific operations it's designed for, it travels on very steep dip angles, which in this case means that there's a strong risk of uncontrollable skidding. And this obviously runs the risk of this machine uncontrollably running into potential nearby workers, or just get stuck against the wall and damage the mining environment. Secondly, there's also productivity implications. So as I just mentioned, the machine might get stuck against the rock face, which means it takes time to remove this vehicle, it might block other vehicles, and it just hampers productivity. Furthermore, if we know something about the traction, we can also use this to optimize the machine's movement. So for example, we can try to optimize certain movements that it uses less battery power, or we can optimize movements to result in the lowest wear on the drivetrain, or things like this. But to do this in the first place, you need some idea of what the traction is. And then if we expand this across a fleet of vehicles, you can start inferring things like mine condition insights. So for example, if you had 2 or 3 vehicles with this technology equipped to it, and they travel on the same mining surface, same areas in the mine, and if all 3 of them tend to see lower traction values in the same area of the mine, that tells you something about the mine, the fact that the mining conditions have changed, or that the traction is especially low in certain areas. Furthermore, if we have traction estimates, this allows us to develop smart algorithms that can adapt to mine conditions. So essentially what we're doing here is we're trying to infer some information, in this case traction, about the terrain, which we can then feed as an input to different algorithms and essentially turn them into terrain adaptive algorithms. And generally this just lays the foundation for a plethora of different technologies we can build off of. So now the more important question becomes, how do we estimate traction? Well, firstly, traction is very difficult to model, especially for skid-steered vehicles where the main mechanism of steering is skidding. So how do you model this? And secondly, we can't directly measure traction from some sensor. It would be very nice, but no such thing sensor exists, unfortunately. So firstly, we can look at physics-based modeling. And as I mentioned, the wheel-terrain interaction is extremely complex, especially so for skid-steered vehicles. So the drawback of doing a physics-based model is not only would it take a lot of time, but it may need to be so advanced to capture all the different mining environments that it's just not feasible. So what we can look at is data-driven techniques. And here we collect data and learn on the data and try to estimate traction from the data. But the problem here is you need labels to this data. So you actually need to measure operational parameters from the machine, but then correlate that to certain traction values. But as I mentioned in the first place, we don't know what the traction is. We need some method of obtaining this. So data-driven methods are likely to be difficult to implement in this scenario just purely because it's difficult to collect the labels, to collect the actual traction estimates for the environment. But if we go and combine both these worlds in what we call a hybrid approach, then we stand a chance. So what we do here is we model the physics, the basics physics of the wheel terrain interaction. And then furthermore, we keep the model updated with the data we collect on the machine. And this may give us an oversimplified version of reality, the simple physics model, but remember it's now continually updated with data, so it remains accurate. So what I quickly want to do is give you an intuition of why hybrid modeling is expected to work in this case. So firstly, we have this physical reality, or the skid steered machine, and we can model some of the physics of this reality. So this we call the known physics. So this we do through the physics-driven modeling process. But inherently, there's going to be some unknown physics or very difficult to model physics that we haven't captured in this physics-driven model. And then what we do is we measure data on the entire machine. This data obviously contains the known and the unknown physics within it. And hopefully by this process of data-driven modeling, we can start to infer some of the unknown physics we missed in our physics-driven modeling process. And once you combine these two worlds, you have what we call the hybrid model. And this you can use to create adaptive, physically accurate predictions. All right. So the question becomes, what basic physics model can we use? And here is a whole algorithm that we developed to do this, but I'm not going to walk you through this today. That's not the main point. So what I'd rather show you is an oversimplification or an intuitive understanding of what we did. So what I'm going to show you now is 3 different vehicles traveling with the same input power, but on different terrains. So let me play the video. And what you'll see is that this vehicle on the left skids a lot faster than the middle vehicle, and the middle vehicle skids a lot faster than the rightmost vehicle. And what I mentioned is that all 3 vehicles have the same power input. So what this tells us is that in this case, the terrain is quite slippery. In this case, the terrain is quite sticky, which means in this case, if we rotate at a fast angular rate, for the same power input, that means the traction has to be quite low. And once again, for the same power input, if we rotate at a slow rate, the traction is then inferred to be quite high. And that's the basic physics of what we modeled in this process. So what type of data do we need to apply the algorithm I glanced over in the previous slide? Well, firstly, we need to know something about the pose, the 3-dimensional orientation of this vehicle. And 2 sensors we looked at to do this were tilt sensors. They work quite well if you filter them correctly. And then also a LiDAR sensor can also give you your absolute vehicle pose. We also need to know something about the turning rate. As you saw in the previous video, that was quite an important parameter. And in this case, you can measure that using a gyro. Or once again, you can use the LiDAR measurements to infer the turning rate. We also need to know how fast the vehicle is traveling, the absolute vehicle velocity. And for this, we can't use GPS because we're operating in an underground environment. So we looked at 2 possible solutions. The one is a ground speed radar. These are typically used in agricultural environments. But the other solution, once again, LiDAR, works quite well. Then we also need to know something about the power consumption. As I said, this methodology relies on the correlation between turning rates and power consumed by the vehicle. So for this, we used current sensors and voltage sensors. And recall that I said this was a battery electric vehicle, so we could use current and voltage measurements to estimate the power going to the wheels. Finally, we need to know something about the wheel rotation rates, and for this you can simply use wheel encoders, which were in this case were readily available on the motors for the four wheels. Right, then I want to get into the concept of actionable insights. So what I've just talked about was estimating traction, right? But is a traction estimate in and of itself useful to us? I would call it an insight, but this insight alone doesn't necessarily give us value as it stands. So as I say here, the insight is not inherently meaningful or actionable. So we need to do something to convert this insight into an action. And this is where we use the concept of digital twins. We believe that digital twins create a logical bridge between an insight and being able to take action on that insight. So therefore, we propose the use of digital twins as vehicles, as mechanisms to ensure that whatever we build ends up in actionable insights. So this digital twin term is quite widely used and we believe widely misinterpreted. So perhaps let us put down a definition of how we interpret it before we continue. So the way we see it is that on one side we have some physical entity, in this case it's our CMTI roof bolting machine. On the other side we have some digital model. Now what I show here is a nice geometric model, a sort of CAD drawing, but note that a digital model need not be something visual. It can be a complicated or simple algorithm also sitting in the back end. All right. Then we need some mechanism to join these two. So we need a physical to digital updating process. And what this does is it measures the physical state and it translates it to a digital state that can then be used. And once it gets to the digital model, the states get optimized and then that information needs to get fed back to the physical entity on this side. So this then we call digital to physical updating process. And the way we update the physical entity can either be through human action. So our digital model can generate an actionable insight that the human then actions, altering the physical reality, or this digital model can create an actionable insight that goes straight into something like a control system, which then automatically alters our physical entity. So what's really important to realize here is that not only is data flowing to our digital model, but crucially, an actionable insight has to flow back to our physical entity, and this closes the loop, allowing continuous optimization of our physical entity. All right. So let me walk you through our process of building this digital twin. Firstly, we developed a geometrically accurate model of our CMTI roof bolter to allow us to estimate the wheel forces. Estimating the wheel forces is paramount to this whole traction estimation process. So on the one side, we had our physical entity and we had CAD drawings of this entity, and we were then able to draw up 3D models of this entity in an environment we call Simscape. It's a MathWorks product. But currently this model is only geometrically accurate. It has no other properties like mass associated with it. So to get accurate masses associated with these geometrical models, we had to do a double lift test. So essentially we lifted the vehicle on the one end, we measured the force, and we then lifted the vehicle on the other end and also measured the force on the other side. And through this process, you can solve the mathematics to figure out not only what is the mass of the vehicle, but where does the center of mass of this vehicle lie, at least in this longitudinal axis. And we were able to find the center of mass location as well as the total mass of the vehicle, so around about 4.6 tons. So now we can take our geometric model and we can assign different masses to each of the geometric blocks. The problem however, is that we only measured the single quantity, so the single mass and its location. We need to break this big mass block up into its constituent parts. And the way we did this was to make a few mathematical assumptions and assume certain things about the density of different components, etc. But doing this, we were able to solve for each of these masses, and essentially these are the masses that we then obtained and then built into the model. All right, so we have all 7 different mass values. Right. Now what we can do is we can take this model we've just designed and we can simulate various scenarios. So we can place this vehicle, we can simulate it under various roll and pitch angles. So let me perhaps just move forward a bit. So what this shows is we iterated over different pitch, rear roll, and front roll angles. So pitch, I'll show you now, but the rear roll describes this back side of the vehicle's movement. The front roll is the front side of the vehicle's movement, and the pitch is the overall upwards or downwards trajectory of the vehicle. And we iterated through all possible combinations within quite a large envelope of angles. And this is essentially what I'm showing here. So this is all in simulation space. And we then logged the normal forces on each of these 4 wheels. All right. And this gives us a lookup table. So I'll just let this finish. This gives us a lookup table where we can input a rear roll and a pitch angle, for example, and then go read off the corresponding force for a given wheel. This is for the front left. Each wheel has its own profile. But obviously this is a 3-dimensional input space. So we have rear roll, front roll, and pitch. It's just impossible to plot all 3 axes and then the force. So I'm showing you 2 axes versus the force. But what I'm essentially trying to communicate here is that for any given combination of input angles, we were able to infer with quite a smooth surface the corresponding wheel normal force. So what this allows us to do is to input our vehicle pose and output the normal force at each wheel, which is quite useful. We've created a virtual sensor essentially that converts pose measurements to wheel force measurements. And just to show that we trust this model, we did the mathematics for one of the known cases, one of the known poses, and this is the red curve, the red parabola, and then we compared it to what the simulation result gave us. And you can see these blue dots follow the red curve perfectly. So we have strong confidence that these curves that generated are accurate and they align with what we expect from our force calculations. Okay, so the question becomes, do we now have a digital twin? We have this model that moves in the same way the real model does, not just in articulation space, but also the wheels. And to answer that question, let's revert back to our definition of a digital twin. So yes, we have a physical entity, great. And yes, we have a digital model, great. Do we have a physical to digital updating process? Does a change in our physical entity reflect in the digital model? Well, the answer is no. So there's no link between our physical entity and the digital model at the moment. We've only calibrated our digital model, but there's no link keeping this model updated continually. So the solution is to update this digital model with data from our physical entity. So in this video, I'm going to show you now, let me perhaps just jump right in. We take various streams of sensor data on the real machine and we feed it to this well-calibrated digital model. And we then apply the sensor readings to this model. So if this wheel was measured to rotate 90 degrees, this wheel will rotate 90 degrees at the same time. And what we also plot at the backside here is the trajectory the machine followed. And what I'll show a bit later in the video is the sort of dashboard at the top of the model. And perhaps I can mention something about terrain. This terrain model was generated using the LiDAR sensor at the top of the vehicle. Not that it's relevant for this algorithm, it's just a nice to have. It aids in the visualization. But perhaps let me now quickly scrub through the video. So what I want to draw your attention to here is you can see as the vehicle moves, the sensor data is being updated in this virtual space. So we can see now it wants to move forward at this velocity, at this yaw rate or rotation speed essentially. Alright, that's more or less all I wanted to show in this video, is that we have this digital model that's mirroring reality with real-time data being fed into it. So do we now have a digital twin? Well, we do have our physical to digital updating process. That's a big plus. But do we have something in our digital model that is influencing our physical entity? And the answer is no. Nothing that happens in the digital space influences this physical entity. So we don't have a digital twin yet. In fact, we call this a digital shadow. Our digital model is shadowing reality, but it's not doing anything to influence the physical entity. All right. And the reason we can make this claim is that our digital model is not generating any actionable insights. There's nothing in this model we can act on. So the solution is we need to take this continually updated model and do something useful with the information. And this now brings us full circle back to the concept of traction. So firstly, let's quickly discuss the concept of a traction ellipse. This ellipse defines an envelope of traction that each wheel experiences. All right. And then this red dot defines the current traction that has been used up by a certain wheel. So when the current traction exceeds this envelope, that is when a wheel is expected to slip. All right. So firstly, how do we define this envelope? Let me just get my marker. How do we define this envelope? Firstly, we need to know something about the wheel normal forces. Now, as I showed you earlier, we went through quite an extensive modeling process where we are able to convert our vehicle pose, so the roll and pitch angles, into a vehicle or into a wheel normal force. So this is something we have. That's great. The other thing we need is estimates of traction coefficients. So mu x represents the forward direction traction and mu y represents the sidewards traction. And this is what we inferred using that algorithm that I skimmed over earlier, that correlation between power input and rotation rates of the vehicle. So these we can infer from those relationships, and these are enough then to define our traction ellipse. Then we can estimate what our current used up traction is, also based on our pose sensors and just basic mathematical relationships, basic physics. All right, and then we can, sorry, I should have shown these earlier, but I've just discussed this. We can then interpret this horizontal distance as how much traction remains in our sidewards direction, right? And similarly, this distance tells us how much traction remains in the forward direction. Okay, so now what we did is we took this same continually updated model that I previously showed you, but now we overlaid these traction envelopes as well as the currently used up traction points. So you'll see as the vehicle moves, these points move around because traction is being used up, but also as the vehicle moves around, the traction ellipses update. So you can see they're actually shrinking quite slowly because traction is being updated as the vehicle turns. And you can see when this dot nears the envelope, it actually goes red, warning the operator that your wheel is about to slip. So now what we've done is we've taken this continually updated information we previously had, and we've converted it into something an operator can take action on, these ellipses with these dots. So for example, when an operator sees this dot go red, he knows he should probably slow down the vehicle or turn a bit slower. And there's multiple factors that influences these envelopes. As I mentioned, it's wheel normal forces. So if this vehicle is traveling on a slope, these envelopes will naturally shrink, showing the operator that they have less traction to work with. Alternatively, the faster the vehicle moves, the further back these dots will go, for example, like right now, and the operator can see they're probably driving at a good speed now, but they probably shouldn't go much faster, or else they're at a risk of slipping. The other thing I'd like to draw your attention to is that part of this modeling process, we also got what we call a motion resistance coefficient. And this is what I plotted on this trajectory. So what we can see is when the vehicle traveled downhill, it was actually quite a low motion resistance, or the green values. And then round about here, the vehicle got stuck in the mud. So you can see there's quite a high motion resistance. And then eventually it got itself unstuck, came around the corner, and stuff dried out and got a bit more flat. And then the motion resistance assumes a much more neutral value, the orange. So not only did we get traction estimates from this process, we also got motion resistance estimates, which are also useful to the operator for interpreting how this vehicle is experiencing the terrain. So what I would argue is that this digital environment you see now is actually useful. It creates a visual demonstration of the available traction, and this the operator can act on. So therefore, we've converted the insight of traction into something we can take action on, which we call the actionable insight. And this, in turn, is what closes the digital twin loop. Let me just pause this quick. So now we still have our physical to digital updating process, but crucially, our digital model is informing our physical entity through human action. And note that nothing stops us from taking this intelligence, these red envelope warnings, and just converting them straight into control system signals, telling the control system to slow down. Okay, so looking towards the future, technology like this allows us to do quite a few things. So to look at 4 examples, we can start to do energy optimization. So we can start to plan trajectories based on our knowledge of the traction to use the least amount of energy. All right. We can also use these traction ellipses to equally distribute loads across wheels. So you might have seen from previous examples that the front wheels had a larger envelope of traction compared to the rear wheels. And this is because the center of mass was a bit more forward biased than rear biased. So this essentially means we can apply more torque to the front wheels compared to the back wheels, and in doing so obtain a faster traveling speed without increasing the risk of slipping at any of the wheels. We can also do torque adaptation. So here we can also adapt the torque between wheels to minimize drivetrain loads, for example. And then finally, I've mentioned this previously, if we apply this technology across a whole fleet of vehicles, we start to detect hazards in the mining environment. So not loss of traction just between the machine and the mining surface, but if it happens across all machines, that tells us that something is wrong with the mining surface. There might be a lot of dust or a hydraulic leak or water that wasn't there previously, but you can start to gain fleet insights from technology like this. All right, so there's 3 key takeaways I'd like to leave you with today. The first one is that traction estimation is important and possible. And I think the takeaway for this block is that this traction estimate gives us actionable insights, at least in the right context, that allows for safer and more productive mining of these vehicles. Secondly, is I'd like to remind you that what we followed here is what we call a hybrid approach. It's modeling physics, but also keeping this physics updated with data as it becomes available. So hybrid modeling is quite a powerful paradigm, and in this case, it was a sensible approach to estimate traction. Finally, just having traction and getting that traction through hybrid modeling does not leave us with anything we can act on. It's only when we put it in a digital twinning context where we try to close this loop, try to generate an actionable insight, that it becomes truly useful. So follow-up steps for this research. Well, we've just laid the foundation for a lot of future applications. So in the previous slide, I showed a few more applications you could extend this to, and these are logical next research steps. So these are the sort of things we're looking at to extend towards. But then also next steps is to get industry partnerships in this digital twinning space. So we really see digital twins as a vehicle or a mechanism that allows us to build technologies that are truly useful to industry for the sole reason that they generate actionable insights. So if this video interests you and you have applications in mind, please reach out. We are doing a lot of active research in this field. Before I conclude, I'd also just like to take a broader look at how digital twins fit into the bigger picture of SAMERDI, at least in our eyes. So, and how does RAMS, or the research activity in mechanized mining systems, fit into this whole digital twin paradigm? All right. What you see in front of you is a framework we developed that defines digital twins with its various types and properties. I'll say a bit more about that in the next slide, but for now it's just important to realize the main dimensions. There's the physical entity, the digital model, the physical to digital updating process, and the digital to physical updating process. The rest is just a bit more, a few technicalities. Right. So the way we see it is that on the physical entity side, this is where data gets generated and handled and processed and things like that. So we see this as something that the RTIMS program is really strongly focused on, and this is where their skill set is. So this is sort of RTIMS domain. On the other side, this is where we build models to do stuff with the data, to infer insights, and not just insights, actionable insights. And this is sort of where we see RAMS, as well as some of the other programs like Locum and AOK. And then obviously there's going to be some overlap where data has to be converted to or physical states has to be converted to digital states. And in this interface is where there's scope for collaboration between programs like RTIMS and RAMS, right? But once we have this digital state and we optimize it, this needs to be communicated back to the physical entity. And this is not always just a purely data-driven technique. Sometimes humans are involved. And this is where we see SATCAP becoming an important research activity, where collaboration is also necessary to inform how we can best take the insights we generate in the digital modeling space and convert them in a human-friendly manner into something that can then alter the physical entity. So for example, in what we showed today, converting this traction estimate into an actual traction envelope with warning signs that operators can act on. So in summary, what I hope to show here is that the digital twin paradigm we follow also reflects the sort of layout of the various research programs at SAMERDI, at least in our perspective. All right, so if the digital twinning framework was very interesting to you, I'd invite you to scan this QR code. This takes you to an article we wrote on this whole topic. Otherwise, you can get in touch with us directly. Here are some emails. And yeah, I hope this was informative and that you understand the difference between just a digital model, which is just a calibrated digital entity, a digital shadow, which is updated from sensor data but does not alter the physical entity in the other direction, and then the digital twin, which closes the loop with actionable insights. Thank you.